Assalamu alaikum. Inshallah, in this video, we will study the development of the microstructure in iron carbon alloy. Here we have an iron carbon alloy, Fe carbon, of composition 5 weight percent carbon. In this phase diagram, here we have a 5% carbon. This x-axis represents the composition of the carbon. So 5% carbon or 95% Fe. Okay. Here 0% carbon means it is pure Fe, pure iron. Make a schematic sketch of the microstructure like what we did in the previous video to draw the microstructure that would be observed for conditions of very slow cooling. So you will start from a temperature, then you will cool very slow at the following temperatures. And the reason to do this is to have a stable microstructure, which we usually have in the phase diagram, which we only have the stable microstructures. Draw you have the temperatures 1175 degrees Celsius, 1145 degrees Celsius, and 700 degrees Celsius. I draw three lines that represent this temperature. We have 1175, which is above the eutectic line, this line, because it converts from a liquid to two solid phases, which we call it gamma, which is the austenite, and Fe3C, which is the cementite. Okay. So here we have the eutectic reaction. So I have a temperature above the eutectic reaction, the eutectic line, which is 1175 degrees Celsius, which is higher than 1147 degrees Celsius. And also I have a temperature 1145 degrees Celsius, which is approximately below the eutectic line. So I have a temperature above the eutectic line and a temperature below the eutectic line, and I need to draw the microstructure for each one of them. And also I have a 700 degrees Celsius line, which is below the eutectoid line. The eutectoid line, this line, the 772 degrees Celsius, we call it the eutectoid line. Okay, and this point that has a concentration 0.76 carbon, this one we call it eutectoid point. Okay, the eutectoid reaction happens that you have a solid phase, or for example, which is austenite, and this austenite then converted to another solid phases which are alpha and cementite. You have alpha this region and cementite in this region. So the austenite converted to this region, which is alpha plus Fe3C. Okay, if you are exactly below the eutectoid point here, you will have a lamellar structure of alpha plus Fe3C. Okay, you will have different let's assume that the red one is the cementite and the white one is the alpha. Okay, so you'll have the lamellar structure exactly under the eutectoid temperature, similar to the eutectoid point. Okay, this one, the red one, is Fe3C, and also the white one is alpha, the ferrite, we call it ferrite. If you are in the right region, right to the eutectoid point, we call it hyper eutectoid, and if you are on the left, we will call it hypo eutectoid. Okay, if you are in the right, what will happen that you will have, like similar to the eutectoid point, you will have particles for Fe3C. So you'll have particles for Fe3C. And if you are in the left of the eutectoid point, you will have lamellar structure also, but you will have particles or the primary particles of alpha. Okay, so you'll have alpha. This one is alpha, and the white also region in the lamellar structure is alpha. The red one is Fe3C. Okay, the cementite. So that is similar to the eutectoid, the eutectic point, the eutectoid point, the difference between them, that one is from liquid to two solids, and the other one is from one solid to two solids, okay, alpha and cementite. Okay, so now I have in the question a composition which is 5% carbon. So I will draw a line that represents this composition of the carbon. Okay, this line will intersect the temperatures line, the three temperature lines. So I will have a point here, let's call it point 1. I will have another point here, let's call it point 2. I will have another point here, let's call it point 3. Okay, now I need to draw or to sketch the microstructure and then label the phases. يعني the phase, is it gamma, cementite, Fe3C, ferrite, alpha, or what? Okay, and their compositions approximate. When usually he says approximate, and usually what we did, we approximate that whenever we have a temperature below or above the eutectic line, we approximate the composition to be the compositions at the eutectic line itself. And also we do the same thing for the eutectoid line, and we will use the lines already mentioned or indicated in the figure or in the phase diagram itself. Okay, so let's start with the first point. The first point is here above the eutectic line. Okay, so it is in this region, and I know this region, the right region, if you complete the phase diagram, you will have something like this. This one is the cementite, Fe3C. Okay, so the right side is the cementite, and it is mentioned here if cementite F3C if you go to the right. Okay, so it is in this region, and in this region I have liquid. So point 1 is a mixture of two phases which are liquid plus cementite Fe3C. So it is in this region. So if I want to draw the microstructure for point 1, I will have liquid. Okay, let's put it outside the letter, and I will have Fe3C as particles. Okay, so this one is Fe3C, and the white region is the liquid. Okay, L. And also he asked for the composition when we said we will approximate, so I will approximate this one. يعني if I want to take the composition of the liquid, I will move until I touch the boundary of the liquid region, then I will go down. Let's say it is approximately 4.7. So the composition 4.7 of carbon يعني for the liquid. So the liquid phase has 4.7 weight% carbon. Okay, so يعني the iron carbon alloy existed as a liquid phase with a carbon composition of 4.7 at this point 1, and for Fe3C I have 6.7 weight% carbon, because if I want to calculate the weight, the composition, I will go to the right, then I will go down, I will have this value 6.7. So it is 6.7 for the carbon for point 1. So that is for point 1, it is easy. What about point 2? Point 2, it is below the eutectic temperature. Okay, so it is in this region. This region is gamma plus cementite, austenite plus cementite, gamma plus Fe3C. So we say that always when we are below the eutectic line or the eutectic temperature, we will have the lamellar structure, and since this is the point of the eutectic point, that is the eutectic point, and we are to the right of the eutectic point, we are in point 2, so I will have particles for the cementite because it is in the right. So I will have not only the lamellar structure, I will have also another particles for the phase that is in the right, which is Fe3C. So if I draw the microstructure, let's draw for example the grain boundaries. It will be something like this, and I will put on the green boundary the particles of the Fe3C. Okay, then I will draw the the lamellar structure. It will be something like this. Okay, so I have this one. The circles or the spheres are the primary Fe3C, and I will have also this one, the red line from the lamellar structure is also Fe3C. So this one also represents the Fe3C. So Fe3C exists as layers of in the laminar structure, the red line of the layers is Fe3C, and also it is the spheres or the circles, which is the primary Fe3C. For the white region, this one is gamma, the austenite. Okay, let's complete also here, also the laminar structure. I have also gamma, the white one is gamma. And in order to calculate the composition from point 2, if I went to the right, then I went down to the x-axis, the composition for Fe3C for both, yani for the primary and from the eutectic Fe3C, they will have 6.7 weight% carbon. He didn't ask for to calculate for each one of them alone, for the primary alone and for the eutectic alone. So we will take the total composition for the Fe3C in point 2. And for gamma, I will go to the left until I touch the boundary of the gamma region, the austenite. Then I will go down, or already it is mentioned in the we said we will approximate, so I will approximate to the eutectic composition. So it is 2.14. So I will have the composition is 2.14 weight% for the carbon, and the remaining is to calculate for 0.3. 0.3 is under the eutectoid. This time is eutectoid. It is austenite converted to two solid phases, which are alpha ferrite and Fe3C cementite. So I will draw the microstructure, and we said it is similar to the eutectic. You will have also a laminar structure, but since we are in the hyper eutectoid region, so we are to the right of the eutectoid point, then I will have particles of Fe3C. If I was in the left, then I will have hypo eutectoid particles for ferrite, but here for 0.3 I have only for Fe3C cementite. So I will draw, for example, the grain boundaries, and then I will put the particles of Fe3C. Okay, then I will draw the lamellar structure also. It is similar to the previous one, but instead now the white region is alpha, not gamma, because gamma is converted to alpha plus cementite. Okay, this time the white region is alpha, not gamma. Okay, and you have to specify in the exam which one is gamma, which one is alpha, which one is cementite, or in the eutectic alloys, which one is liquid, which one is alpha, which one is beta. Okay, so I will just indicate the composition and the phases. So here I have this sphere or this circle particles, and also the red line in the laminar structure is both of them are Fe3C with also, if I went to the right, I will reach the end of the x-axis, which is 6.7 weight% for the carbon. So I have 6.7 weight% for the carbon, and this white region is alpha. And if I go to the left until I reach the boundary of alpha, this is the alpha region, this small, very small region, and it gives you that 0.002, that is the solubility يعني limit, or the boundary, the composition of the boundary of the alpha region between the alpha and alpha plus Fe3C. So alpha, the composition is alpha is 0.022 weight percent of carbon. Also, if you are asked about the peritectic reaction, the peritectic reaction is that you have a solid and liquid, like this one. You have austenite, which is solid and liquid. Then they are converted to austenite, which is only one phase, solid phase, or the opposite, that is, we call it peritectic reaction. Okay. So that is it for the development of the microstructure in iron carbon alloys.